Hello there. Today we're going to just have a nice easy lesson, and we're just going to go over the common vocabulary terms that are used within this unit. And we're going to talk about the various common definitions and vocabulary that is used within this unit, just so you have a better time navigating exactly what you need to do when you work through the exercises. So the first term we're going to go over is this term called relatively prime. Okay, now this term, let me just grab my pencil here, corresponds to two numbers that have no prime factors in common. And this is important, of course, but it has some important implications when it comes to the GCF and the LCM. Let's talk about them. All right. So, for the, let's do the LCM first. So for the LCM, right, if we have no prime factors in common, this always means that the LCM is going to be the multiplication of the two numbers. Okay, so whatever two numbers you have, if you multiply them, and if they're relatively prime, they will give you the LCM, right? Let's also talk about the GCF quickly. So for the GCF, right, the GCF is very simple. It's always equal to 1. In fact, sometimes this is actually used as the definition for relatively prime. So this is commonly just abbreviated as the definition for relatively prime, where the GCF is equal to 1, right? So if we do a quick example of two numbers that I know are relatively prime, so for example, let's say we did 6, right, and we did 7, right? Now, the prime factors for 6 are obviously 2 times 3. We don't need a curly bracket there. And for 7, of course, it's just equal to 7, because we know 7 is actually prime. But obviously, there are no prime factors in common. And we can see that right here, right? Where we see that, 2 and 3 are not a member of the prime factorization set of 7. And 7 is, of course, all by itself, right? So if we were to find the LCM, right? And you can do this using the old techniques as well. But I'm going to do this quickly. The LCM is going to be equal to 42. No other number is going to have a 6 and a 7 in it, and the GCF will be equal to just 1, right? And you can confirm this. I'm going to leave that as a homework exercise. You can confirm this by doing it sort of the old way, the actual GCF and LCM way that we've talked about in the previous videos. Okay? So let's keep going. Okay, so the next term I want to talk about is composite number. This is actually a very straightforward term. So a composite number is any number that is not prime. So in other words, it has 3 or more factors. We did 6 on the previous slide. That is also a composite number. So it's just any number is basically prime, or it's composite, or it's like 1 and 0, which are just categories of their own. I want to cover 2 key divisibility tests that are common. Because we're dealing with prime factorization, typically the sort of the uncommon ones, like I would say stuff like, 5 is easy, 2 is easy, but if you look at the common ones like 2, 3, 5, 7, 11, and 13, 7 and 13 automatically just don't have any, so that's just out. 3 is there. And 11 is there as common divisibility tests that aren't exactly intuitive, right? So if you think about 2, it's easy. It just has to be an even number. 5, again, ends in a 0 or 5. Very straightforward. But these two are sort of not intuitive, so I want to go over them quickly. A number is divisible by 3 if the digit sum is also divisible by 3, right? So it might be helpful to do another quick example here. Let's do one. So for example, I have here, let's go with 111, right? To quickly check if that's divisible by 3, you just do 1 plus 1 plus 1 which is equal to 3. And we know that 3 is divisible by 3, right? So 111 is divisible by 3. This is correct. And if we just check using our calculator, 111 divided by 3 is 37. So 37 times 3, actually we'll put it the other way. 111 divided by 3 is equal to 37. There's a little happy face for you. Okay? Now the next one is the divisibility test for 11, which is definitely a bit more complicated. So let's talk about that. Okay, so this is another good number to basically be on the lookout for, because it's definitely not an obvious divisibility test, but once you get the hang of it, it gets a lot easier. So let's quickly go with this number, 172,656. So if we do that, the first thing we want to do is calculate the alternating digit sum. So what do I mean by that? So 172,656. So we're kind of going to jump around here. We're going to go 1 plus 6 plus, we're going to go 1 plus 2 plus 5, and then 7 plus 6 plus 6, right? So 1 plus 2 plus 5 is equal to 5, 6, 7, 8, and then 6 plus 6 plus 7 equals to 19. Right? And we know that 19 minus 8 equals to 11. And of course, we know 11 is divisible by 11. Right? Which means that this number, 172,656, is divisible by 11 as well. Okay? So that's the divisibility test for 11. Twin primes, a very easy concept. It's just two primes with a difference of 2. Let us emphasize that right there. That is very bad. Let us just use the highlighter here. Bingo. So 17 and 19 is a good example. These tend to be pretty rare because normally when you do that, you just end up with two odd numbers and there's a factor somewhere. But there are some examples of twin primes. We know 5 and 7 is another good example of two pairs of twin primes. Just a nice number that they like to throw out there. So definitely know what a twin prime is. Proper divisors are all the divisors of a number, excluding the number itself, but not excluding 1, right? So let me give you an example of a proper divisor. So let's just take an example of 6, right? So 6, the divisors, by the way, another term for divisor is factor. So we'll just use those two terms interchangeably, okay? So the factor of 6, pretty easy. It's just 1, 6, 2, and 3. I've put them in pairs here. And what we need to do now is we just take this 1, 6, 2, 3, and we want to figure out whether this is these are all proper divisors. So all the proper divisors are everything here except the number. So we're going to kick this one out, and the proper divisors of 6 are going to be 1, 2, and 3. Okay? So that is the concept of proper divisors. Finally, our related concept of the perfect number, which is the sum of all the proper divisors, right? So let's look at 6 again, because 6 is an example of one. So we already talked about the proper divisors of 6, which are 1, 2, and 3, right? But coincidentally, 1 plus 2 plus 3 also equals to 6, right? That's a 5 plus 1, which is equal to 6, which means 6 is absolutely an example of a perfect number, okay? That was a bad arrow initially, but I think it recovered pretty well there. The final term I have for you today is consecutive numbers. These are just numbers that are next to each other. Very easy, right? So 1 plus 2 plus 3, those would be consecutive numbers, right? So if we're looking at, for example, 5, 6, and 7, these are consecutive numbers. I'm going to erase 1 plus 2 plus 3 because you don't have to be adding them, right? If you're just looking for a list of consecutive numbers, 5, 6, 7, perfectly fine. They're just the numbers that are next to each other. Okay, that is it. We have now covered everything we need to cover for the FMP module. Keep tuned to Google Classroom because there's going to be one last post about how to navigate the rest of the work. But now you can try everything you need to try, and you're good to go for this module. All right, have a good one.